Hello everyone. In this video, I'm going to solve one problem from chapter 1, and the problem number is chapter 1, 1.1. It is one of the example problems. I thought it is important that you understand the basics of how to use the equations. So in this problem, the problem statement is a 10 centimeter diameter copper ball, this diameter of the ball is 10 centimeters, is to be heated from 100 degrees to an average temperature of 150 degrees. So from 100 to 150. So it better be put in an oven or something, and they're heating the ball. And it takes 30 minutes to reach this 150 degrees. So the way when you're heating, you're transferring the heat basically, right? Taking the average density and specific heat of copper in a temperature range, what this temperature range given is rho is 8950, which is density of copper, and also specific heat at constant pressure is 390.395 kilojoules per kg degree centigrade. And so this is the description of the problem. All the relevant information is given, and the question is there is being asked is the total amount of heat transfer to the copper ball. There are three questions are there. Part 1 is what is the total amount of heat transfer to the copper ball, because you're raising the temperature from 100 degrees to 150 degrees, so you had to put heat into the copper ball to raise the temperature. So thus he wanted total amount. And then the next question is average rate of heat transfer to the ball. So now it is a rate here. That means time is involved. Here there's no time involved. And the third one is the average heat flux. And heat flux is how much heat is being transferred per unit surface area. We'll go into the details. So what I have done is I am going to slide a paper so that you have all the relevant information captured here. And what I have done is put down problem number first. Diameter of the ball 10 centimeters, which is equal to 0.1 meters, because our units have to be in meters. And temperature, the time it took, it is delta T. It's not temperature, it's the time it took. Delta T is 30 minutes. We want them to be in seconds, so I convert into seconds. And T1 is, we know the temperature 100 degrees, and T2 is the temperature it has raised from 100 degrees to 150 degrees. And the density he was given 8950, we got it, and specific heat is given. Yeah. So the question, let's start with the question of the total amount of heat transfer to the ball. That was the first thing we're trying to figure out. Okay, so so to start the question, so this is just to give an idea, the units and things like that. Total amount is always in kilojoules, or kilojoules is the one we're using it for this. And the equation for the kilojoules is Q equals, that means basically when you're heating it, what are you doing? You're changing the internal energy. So that is equal to delta U. And so the internal change of internal energy is given by the equation mass times specific heat times delta T, that is T2 minus T1. Are we good so far? And so here mass, to find the mass of the copper ball, we have to multiply it with the volume times density. So in the side you can write density, mass equals density times volume. So density is given, right? So you plug the value there, and so let's go ahead and do it. Volume of the copper ball is, let's start with the density first, is given 8950. Kilojoules, kgs per meter cube. And the volume is, how do you find the volume? Volume of the copper ball, it's a sphere, right? For the sphere, the volume is pi d cube over 6. This is diameter over 6. So what is it? We know the diameter. So let's plug that value, 8950 kgs per meter cube, and 8950 meter cube times pi times 0.10 meters, that is whole thing squared, divided by 6, and you will come up with, if I crunch it, 8950, so it will come close to 4,680 kgs. So that is the mass. So all we have done so far is just solve the we found the mass. Now to find it, the heat transfer, that is equal to, mass is 4,680 kgs. If you simplify, if you look at meter cube get cancelled, only thing is left kgs, and Cp is given, that is specific heat, times 0.395 kilojoules per kg Kelvin, and T2 minus T1, 100 minus 150, 50 degrees. So if you crunch the numbers, it comes close to 92.6 kilojoules. So that is the total heat. So we just solve, this is, you could call it as a Q, and is one answer right here. So now going back and reflecting, what is T2? 150 degrees. T1, 100 degrees. That's already subtracted. Cp is given. We don't have to go and look for the tables. And density is given. Mass we had to find out. How did we find out the mass? Rho times volume. So we got that. So let's go to this is part A is done. Part A solution. Let's go to the part B. What is part B? Rate of heat transfer. I think putting average rate of heat transfer. So how do you find the average rate? Here's the formula. Okay. So whenever you are using an average, that means time is involved, is nothing but total heat divided by delta T. So we calculate total heat already, 92.6. That is kilojoules. And delta T, if you remember delta T, it is taking 30 minutes, right? So that means it took 1800 seconds. That is your delta T. So you go back. And plug the value, 1800 seconds. So if you solve that, you will come up with 0.0514 kilojoules per second. Or you can write it as 51.4 if you multiply in terms of joules, joules per second, and joules per second is also equal to watts. 1 joules per second is a watt. So you multiply this one with 1000 and you get this one. Okay, so far so good. So one unit you have to remember is watts equals joules per second. So if just away from this problem, we use in our houses electric bulbs for the light. So if they specify, for example, this is nothing to do with this problem, I'm just giving an example in a box here, and if they say I have a 100-watt bulb, 100 watts bulb, what does it mean? That means it is producing 100 joules of electricity, heat per second. That's what it means. So I just want you to understand this definition, how it works, okay? And then moving further, the last part of the question is to do with heat flux. Heat flux. So what is heat flux? Heat transfer per unit area. So to use the heat flux, the equation for the heat flux Q, represented by Q average 1, is equal to, we need the average rate of heat transfer. It should be average rate of heat transfer. Average rate of heat transfer. So rewrite the whole thing. Average rate of heat transfer per unit area. So how do we get that? So I gave you the formula. So you already calculated Q dot, average rate, that is divided by the area, surface area of what? The sphere, the copper ball, right? It is in a sphere shape. So the surface area of copper ball, we know, we already calculated this average rate of heat transfer, which is 51.4 joules per second, divided by the area of the surface area of the sphere, is given by this equation pi d square. So you plug those values, 51.4 joules per second divided by pi, and the diameter we know, which is 0.1 meter square. And if you solve this, and you'll come up with a number 16.36 watts per meter square. So all three parts were done, but what I'm trying to emphasize here is, let's summarize this. This is very important to summarize, and so that you have a clear understanding of how to use these formulas and what is the average rate of heat transfer, what is the heat flux, and so on and so forth. So first is total heat. The formula for the total heat is Q is equal to mCp delta T, mass times specific heat times temperature. And the unit for this one is kilojoules or joules. No, not seconds. There's nothing there here. Okay, that's one. Second is rate of heat transfer. Rate of heat transfer. You can, we are everything is in average, so rate of heat transfer. That is Q dot, and the formula for this one is Q over delta T. Or you can, so that here the units are joules per second or watts. Remember what I told you? Watts, the formula for the watts is here. It goes joules per second. So you just convert it. And the last portion of it is heat flux. What is heat flux? Q, small q, is Q dot, the average rate of heat transfer, divided by area. And so area is in meters square. Obviously, the unit for this one is watts per meter square second. So this is how you solve the problems. But I think important thing, key thing is to understand the formulas and how to apply them. And and also understanding the meaning of rate of heat transfer and also the heat flux. Heat flux is, so that means if you go and measure the heat on the surface of the thing, you should see a number close to this one. It will vary a little bit, but it is that's what you are about. This is because the average number here, because everything is average. Remember what we did? Average, okay. So going back and reviewing the problem one more time. So here, luckily, he has given you density, and so you don't have to go and look for the tables. But you have to make sure conversion in meters and also time in seconds. That's how the joules are defined. Remember, joules per second, watt equal to joules per second. And temperatures are given. So that means showing so much heat you have to add to the copper ball to raise the temperature from 100 degrees to 150 degrees. So that is a statement. So then using using the equations and trying to plug it in, and also when we talk about how do you find the mass, that means you need to know the formula for the sphere volume, and also to find the heat flux, you need to know the surface area of the sphere. So this has to be in your back pocket when you're trying to solve this problem. Okay, and I hope this makes it easy for you. And but typically, these are the problems. You'll see some very similar problems in the homework. So this will also prepare you for the homework. Okay, thank you. Bye bye.